After the discussion of thermodynamic potentials, I would like to conclude the chapter on thermodynamics, a very compact treatment of classical thermodynamics, with a brief discussion of various thermodynamic coefficients. Thermodynamic coefficients are often the quantities that you measure in an experiment, because coefficients characterize, these thermodynamic coefficients characterize how a system reacts to some external action. So how does the volume change when you change the pressure? How does the temperature change when you supply heat? How does the system expand? How does the volume change when at constant pressure you heat the system, you increase the temperature, and so on. So you perform some action on the system responds by a change of its thermodynamic, its macroscopic data, its thermodynamic variables. You measure that response, and this is captured in these various thermodynamic coefficients. So this is often, the coefficients are what is most easily and most directly accessible in experiment. In contrast, the fundamental equations say the entropy as a function of internal energy, particle number, and volume, which is of great interest theoretically and which we try to derive when we start from a statistical model, from a microscopic model. We calculate the partition function, and then we try to infer this fundamental equation for our substance. This is usually not accessible experimentally. You cannot directly measure the, say, the entropy function as a function of energy, particle number, and volume. First of all, because entropy is not directly measurable. So there's a mismatch between the coefficients, which you typically measure in an experiment, and the fundamental equations that you typically derive from your microscopic model, and you have to bring them together. So you have to seek ways to learn something about the fundamental equation of a substance from the coefficients that you measure. Let me just write down in a few key words what I just said. So these coefficients are important for experiment. They are often sort of most easily measurable. And then you want to use these measurement results for the thermodynamic coefficients to infer something about the fundamental equation, entropy as a function of energy, particle number, and volume, because this fundamental equation cannot be measured directly. Let me start the discussion of thermodynamic coefficients with just a list of important examples that often occur. And in all these examples, I will assume that the particle number is fixed throughout. So I will not write explicitly that in all these examples, particle number is kept fixed. So one example which we have already encountered is the specific heat. It comes in different versions. We have already seen specific heat at constant volume. There's also specific heat at constant pressure. They are denoted by different symbols, either CV at constant volume or CP at constant pressure. And they are defined in the following way. Specific heat at constant volume, you divide by the number of particles, And then you had looked at that on one of the problem sheets, that the proper definition is the amount of heat supplied, so that's T ds over the change of temperature to which this corresponds. So over dt at constant volume. When you have the specific heat at constant pressure, it's the same definition, only that you have this expression at constant pressure. Secondly, there is compressibility. Again, this is a coefficient that we have already seen, compressibility. This also comes typically in two versions. The one that we have seen is the isothermal compressibility, which was denoted by kappa T, and it's minus 1 over the volume, partial of volume with respect to pressure at constant temperature. There's also the adiabatic compressibility, denoted by kappa S, because in a quasi-static process, adiabaticity, so no heat exchange, is equivalent to keeping the entropy fixed. And this is the same definition, only that instead of the temperature, you keep the entropy fixed. Then there is the so-called expansion coefficient, which is typically denoted by alpha, but which you should not confuse with the Lagrange parameter alpha. So this is a different alpha. And it describes how, at constant pressure, the volume reacts to a change in temperature. So it's the partial of volume with respect to temperature at constant pressure. So just this remark, do not confuse with the Lagrange parameter. And one last coefficient that I would like to show you in this list, it has a pretty long name. It's called the isochoric. Isochoric means at constant volume. Isochoric thermal pressure coefficient, denoted here again as a reuse of symbols by beta with an index V, indicating constant volume, and it's defined as the change of pressure when you change the temperature at constant volume. So this is just a list of some common thermodynamic coefficients. And I'd like to make just a few general remarks about these thermodynamic coefficients. This course doesn't allow us, or we don't have enough time to really do many calculations with them. On the last voluntary problem set, there is one calculation that you can do with coefficients, but we'll be content with just a few general remarks about these coefficients. One remark is that thermodynamic coefficients are related to second-order partial derivatives of thermodynamic potentials. Consider the following example. Consider the specific heat at constant pressure. Remember the definition, that's T over N, partial of entropy with respect to temperature at constant pressure. Now the entropy is minus the partial derivative of the free enthalpy with respect to temperature at fixed pressure. Remember in the Guggenheim square that the free enthalpy has as its natural variables pressure and temperature, and entropy is the conjugate of temperature. So when you take the partial of G with respect to temperature, you obtain, up to a sign, the entropy, and here this happens to be a minus sign. But this implies immediately that you can write the specific heat at constant pressure as minus T over N times the second order partial derivative of free enthalpy with respect to temperature at constant pressure. So up to a prefactor, this is a second order partial derivative of a potential. A second remark I would like to make is that there are lots of relationships between the various thermodynamic coefficients. They are often related to each other. Again, let's consider an example. Let's consider the differential of volume. Then very generally, if we consider volume as a function of temperature and pressure, particle number is always fixed, so I don't write this explicitly. There's no variation of particle number, but at fixed particle number, volume can be considered as a function of temperature and pressure. So I can always write the differential of volume as, I can write it as a linear combination of the differential of pressure and the differential of temperature. And the respective coefficients are the partial of volume with respect to pressure at constant temperature times dP plus the partial of volume with respect to temperature at constant pressure times the differential of temperature. I can multiply this equation on both sides with 1 over the volume. This is easy enough. Then I can consider another differential. I can consider the differential of pressure and consider pressure as a function of temperature and volume. So I write this as partial with respect to temperature at fixed volume times dt plus partial with respect to volume at fixed T times differential of volume. And I can solve this for the differential of volume. So I can write this as dV. I do this by multiplying the equation with the inverse of dP over dV, but this is nothing but dV over dP. So this is dV over dP at constant temperature, dP, minus dV over dP at constant temperature, times dP over dt at constant volume, dt. And this equation, again, I can multiply with 1 over the volume. Now compare this last equation with the first line. We have the same term on the left-hand side, and on the right-hand side we have, in both cases, we have two terms, and the first terms agree. So the second terms, so this one and that one, they must agree. They must be equal. Up there in the first line, on the first line, this is by definition the expansion coefficient, alpha. In the last line, we have a product, and minus 1 over the volume times the partial volume over pressure at fixed temperature, this is the isothermal compressibility. And the second factor, the partial of pressure with respect to temperature, at constant volume, that's the isochoric thermal pressure coefficient, which we had called beta V. So you find the relation that expansion coefficient equals isothermal compressibility times the isochoric thermal pressure coefficient. And this is just one out of many relationships that you can find amongst the thermodynamic coefficients. On the last problem set, you will have another exercise where you will derive another of these relationships. Last remark about thermodynamic coefficients: they are often related to statistical fluctuations. So not all, but some thermodynamic coefficients are related to statistical fluctuations. Again, an example that we have already gotten to know, that's the specific heat at constant volume, CV. Here's the definition. It's T over N, partial of entropy with respect to temperature at fixed volume. Now at fixed volume, this is equal to 1 over N times the partial of internal energy with respect to temperature. Because du is TdS minus PdV, but if the volume is constant, dV is 0, so du is simply TdS. So we have this equality here. We can, instead of taking the partial with respect to temperature, we can use the chain rule and replace it by a partial with respect to inverse temperature beta. So we can also write this as 1 over N and then d beta over dt and then du over d beta at constant volume. This partial here, this is minus 1 over kT squared. And then we can exploit that we can obtain the internal energy U from the log of the partition function by taking minus the partial with respect to beta of the canonical log of the canonical partition function. So in fact, this is nothing but 1 over n kT squared times the second order partial derivative with respect to beta of the log of the canonical partition function, which, I write it explicitly, is a function of beta and volume, and you take this partial at constant volume. And we had shown before that this second order partial derivative of the log of the partition function is the variance of the internal energy. So it's related to the size of energy fluctuations, statistical fluctuations of the energy. We had discussed that within our general framework, and here we see once again that this is in turn related to the specific heat at constant volume. So this is one example where a thermodynamic coefficient is related to statistical fluctuations. So to summarize, I discussed 3 remarks about thermodynamic coefficients. I mean, aside from the fact that these are sort of the experimentally often the most easily accessible quantities, we had 3 remarks. One is that they can be obtained from thermodynamic potentials by taking second order partial derivatives, that there are lots of relations amongst themselves, and that some of them are related to statistical fluctuations.